Okay, so in this segment we're going to develop a new tool for magnetostatics. It's applicable whether we have magnetic materials or whether we don't, and that tool is going to be Ampere's law. Now again, we're going to develop Ampere's law in analogy with a similar kind of equation that we use in electrostatics. So in electrostatics we have the divergence of the electric field is given by the charge density, and we can integrate this out over a volume and derive Gauss's law, which tells us that the integral of E dot dA is equal to the enclosed charge divided by epsilon 0. Now this is an equation which is useful in situations of high symmetry, and it enables us to calculate the electric field from charge distributions, highly symmetric charge distributions, spherical charge distributions, planar charge distributions, cylindrical charge distributions, and so on. So we're going to develop a similar kind of tool in magnetostatics, but rather than starting from the divergence equation, of course, we're going to start from the curl equation. Okay, so what I've drawn here is a free current distribution J, which may depend on position in space. I'm going to, for the time being, just drop our distinction between R and R prime. I'm just going to write it as J of R here. And we're going to put in a surface, the surface that I've drawn here, or I've drawn a loop here. This loop actually bounds some surface. It might look something like that. It could be any surface at all bounded by that loop. And we are going to integrate both sides of the equation over that surface. So the dot dA here would be the surface normal pointing away from this surface, and the integral of the curl of B dot dA over that surface is mu naught times the integral of J dot dA. That's just integrating the left hand side and the right hand side over a surface. We can apply Stokes' theorem to this side of the equation, and this side becomes the integral of B dot dl, where the dot dl is around this curve here that is bounding this kind of crazy looking surface that I've drawn here. So this surface looks a bit like a helmet with an open end here, and the left hand integral then is around that curve. The right hand integral becomes the current, total current enclosed that flows through this surface. This is Ampere's law, and if you look at it, it's analogous to Gauss's law in electrostatics. It's useful when we have situations of high symmetry, just as Gauss's law was useful in electrostatics when we have situations of high symmetry. So a classic problem with Ampere's law is to calculate the current flowing in an infinite wire. So let's just do that calculation very quickly. Imagine we have an infinite wire, it's carrying current I, and the surface that I'm going to put in is going to be a circular surface, and that circular surface has its surface normal parallel to the wire and is going to be a surface of radius r. Okay, so in this situation we would write Ampere's law down as in the following way. Okay, so this then is the magnetic field, a distance r, that's radius here, away from the wire. The magnetic field is in the phi hat direction. In order to do this calculation, we have to have a highly symmetric situation where we know from the symmetry and the right hand rule that the magnetic field will indeed be in the phi hat direction. We need that so that we can complete this part of the integral. B is parallel to dl everywhere on this loop, and so the integral of B dot dl is just 2 pi rb. We can complete the left hand side. The right hand side is straightforward because the entire current flows through the surface, and we know from symmetry that it is in the phi hat direction. Okay, so in the next segment we're going to develop Ampere's law for the H field in analogy with our development of Gauss's law for the D field.